measure and the model of the soil. The measure will be modeled as an assembly of bricks with no tension contact interfaces and with a more column friction law on the interfaces. The soil at the moment is modeled as an elastic soil, as an infinite half space, half plane, two-dimensional. The numerical implementation is two-dimensional, but the approach is quite general, can be three-dimensional, and can also be orthotropic, not only isotropic, and also for elastic, for instance. But at the moment, the numerical implementation is developed for the elastic case. The two models need to be coupled along the common interface, which is the interface where the measure rests on the soil. And here the interface also is, must take into account the unilateral contact condition between the two models and also more Coulomb friction. The submodel 1, the model representing the measure, is similar to discrete element method. We have an assembly of bricks. The brick can be, in principle, either rigid or elastic. The implementation and the numerical results I will show consider the brick rigid. The elasticity of brick and interface is concentrated into springs in the interface. Two contact points are considered between each brick and each of the surrounding brick. The pattern of the texture can be any. And also, of course, the contact must be of unilateral type. Only compression is allowed. And the tangential direction, the frictional conditions, the more Coulomb conditions must be satisfied. Now, we can write the total complementary energy in terms of the contact interfaces and of the boundary condition, and obtain the solution in terms of the contact forces between each couple of bricks as minimization of the total complementary energy. This is an approach that is published in a few papers. You can find it in literature. Under the constraints that, of course, there is the equilibrium of each brick, the more Coulomb condition, and here Fn must be greater than 0 if greater than 0 means compression. What about the submodel 2, the soil? For the soil, we have used an approach which is quite common in the boundary element method context. You can solve the semi-infinite space under any load condition on the free surface in terms of forces or displacements by writing an integral equation that involves the integrals only along the free surface segments that are loaded either by forces or by displacement, and some special functions, the capital letters here, that in literature are called as a fundamental solution. Changing fundamental solution, you can change, for instance, the resolution, the solving integral equation from elasticity to orthotropic or to pore elasticity. You can discretize the free surface. After discretization, in our case, we have discretized we have developed the code by using linear elements. And then you can collocate the discretized integral equation in each node. At the end, you obtain a system of equations in which, after applying the boundary condition on the free surface, you get a square system of equations which is linear and simply can be solved in terms of the unknown on the free surface. There are some advantages with this approach. First advantage is that in order to model the infinite sides of the soil, you need only discretize the part of the free surface that is loaded. That in our case is exactly the contact interface between the soil and the wall. Secondly, the infinite sides of the soil is implicitly included in the formulation by the fundamental solution. And third, you can evaluate displacement or in any different point from the discretization on the free surface, or stress and displacement in any internal point as a post-processing step. This is an example of a comparison for an half plane loaded by constant load. Four linear boundary elements are sufficient to get exact coincidence between the analytical solution and the numerical solution. The analytical solution by Poulos and Davis, for instance. A potential cavity or inclusion is included just discretizing the boundary of the cavity, either the cavity or the inclusion with different materials. Now, what we want to do is we have this model solving the problem of the masonry, this model solving the problem of the elastic half space. Now we want to couple them and get the total solution by imposing the unilateral condition on the common interface and more column friction on gamma over bar. Gamma over bar is the contact between the masonry and the soil. Now, the problem is of course nonlinear, okay? The minimization procedure here is quadratic, first of all, and is solved by optimization tool Mosaic inside MATLAB. But it's also nonlinear because you don't know in advance the contact zone between the masonry and the soil. So you need to solve this nonlinear problem in an iterative way. And what we set up was this iterative process in which we start with the solution of the masonry under the condition of a fixed base. We evaluate the forces here, then these forces become traction on the submodel 2. We get the displacement on the same gamma over bar, and we get back to the masonry to recalculate the forces. And this iteration continues until some errors in terms of the, let's say, the displacement and traction between two successive iterations go below a certain tolerance. We also got the suggestion by a paper published in 2003 in which the update solution is not exactly the solution at that iteration, but is a combination of the solution at that iteration and the solution at the previous iteration. This makes the convergence a little bit smoother. The drawback is that you have to define two parameters alpha beta. Now, by solving this iterative procedure, we are able, given the loads on the masonry, to evaluate the final solution in terms of contact forces here, traction and displacement everywhere here, satisfying all the conditions of model 1, all the conditions of model 2, and the contact condition, the unilateral contact condition between masonry and soil, and friction and more Coulomb friction law, and satisfying the more Coulomb friction law in the tangential direction. Now, there are two issues that arise. Here, the model admits as displacement the displacement and rotation of the centroid of each brick, whereas in this model 2, we need a continuous distribution of the displacement. Here we get the contact forces, while here we need to apply a continuous distribution of traction. Vice versa, here we get a continuous distribution of the displacement, and here we have to impose displacement in the centroid of each brick displacement and rigid rotation. So we have these two. Now, how do we solve the first one? How do we pass the displacement, that is the solution of the spool problem 2, as boundary condition to the Masonry model? In very simple way, we get the continuous distribution of the displacement, and we can obtain directly as average and rigid rotation from these 2 points. We can get directly the value on the brick. I go far. We developed a similar strategy, 2 different strategies to pass the traction from the masonry to the soil. I have no time to detail. I can answer some questions afterward. I go directly to the numerical results. First numerical results was developed just to check the performance of the procedure and also to compare the 2 strategies that I had no time to detail. Anyway, if you look at a simple wall with, without horizontal force and with horizontal force on the top, this is the boundary condition, the example, you see here that the inclusion of the soil elasticity allows a crack pattern to be visible that wouldn't be visible in the case of fixed foundation model. Here you can see the distribution of the pressure on the soil, comparison between different strategies and the fixed foundation. The red one is fixed foundation. The continuous black is the pressure for our approach. Similar results for a higher force and for different boundary condition above fixed foundation, below with the inclusion of the elasticity soil. Second example, a semicircular arch. In this case, this arch is loaded by self-weight plus a non-symmetric vertical load just to amplify the differential settlement between these 2 contact area. And here, of course, the fixed foundation approach would not give any differential settlement, whereas here our approach provides, as you can see, a differential settlement and also some hinges occurring due only to the differential settlement. Last example, we just took, in honor of our host, we took a bridge that was investigated in a paper by the colleagues from Padua, the Trigno Bridge River. As a matter of fact, it's multi-span. We focused only to span by applying special conditions on the vertical boundary lines. And here is the comparison. The line above is the results with only the self-weight. Below, self-weight plus 2 axes of Ellery with forces estimated following the Italian technical norm. And you can see here that first of all, we have that due to the elasticity of the soil, the hinges, there are some hinges occurring close to the central pier. We also put a cavity here to simulate very simply. Of course, we are improving the approach with a more advanced model, but this cavity could represent a sort of a scoring. And here, this is this vertical displacement, horizontal displacement, and you can read here the differential settlement calculated with our approach. And finally, this is the results are similar to what is published in the paper I cited before. In our case, the hinges are a little bit closer to the central pier. Thanks for the attention.
Thank you very much, Vincenzo, for a very nice contribution.
I've been on time.
So we have little time just for one question. Any question from the floor? questions, so we can move to the next one then.
Okay,
Thank you very much.
thank you.